For millennia, humans have turned to the sky to tell time. Our planet rotates once on its axis, and we've lived another day. We divide that day into smaller fractions: the hour, minute, and second. But Earth is an imperfect clock. Its orbit and rotation vary slightly from year to year, the kind of wiggle room that makes it incredibly difficult for scientists to do their calculations, or for satellites to send their precisely coordinated communications. That's why, since 1967, the scientific second has had nothing to do with celestial bodies. Instead, it's calculated according to the properties of a cesium atom. When illuminated with laser light under specific conditions, a cesium atom emits microwave radiation, rapid waves of light that crest and dip. That year, the General Conference on Weights and Measures (CGPM), after its name in French, officially defined the second as 9,192,631,770 cycles of that wave. Cesium seems like a random choice. But scientists use it because the atom, one of the smallest units of matter, is about as well behaved as they come. Its radiation won't change, no matter where or when you observe it. It's the ultimate calibration, syncing Earth's timepieces to the universe's clock. Fundamental constants are the closest we have to a universal language. Since then, scientists have defined the meter based on the speed of light, a similarly unflinching universal value. It makes sense to have your measurement system based on true invariance of nature, says physicist David Newell of the National Institute of Standards and Technology. And scientists are now working on re-standardizing 4 more units, the ampere, Kelvin, kilogram, and mole, by measuring fundamental constants more precisely than ever before. Researchers worldwide submitted their final measurements in July to a group of scientists working with CGPM, and they will meet next week to discuss them. By late next year, the plan is for every single unit but one, the candela, to be based on a fundamental constant of nature. Scientists want the universe, not the shaky human hand, to reset our earthly thermometers and scales. For nearly 130 years, the kilogram has been determined via comparison to an impeccably polished platinum iridium cylinder, based on the mass of a cubic decimeter of water. No longer. Starting next November, it'll be calculated from Planck's constant, a number associated with the smallest units of energy in the universe. To do this, scientists first measure the constant using a glorified scale called a Kibble balance, with a known mass on one side and a magnet pulling on the other. Once they nail down that measurement, defining Planck's constant is surprisingly bureaucratic. They submit the measurements to CODATA, a group that works with CGPM. CODATA averages these measurements with statistical methods and then recommends a fixed value of Planck's constant to a committee that reports to CGPM. All units of mass, the kilogram, the atomic mass unit, and even America's sweetheart, the pound, can be calculated from that value of Planck's constant. Don't worry, they'll be so close to current values that you won't have to throw out any old bathroom scales. The committee doesn't just concern itself with masses. Next year, the Kelvin, which is equivalent to the degree Celsius, will be defined by a number known as Boltzmann's constant, which relates the motion of single atoms to a temperature. Right now, the Kelvin is defined by measuring the triple point of water, a temperature and pressure where ice, vapor, and liquid water can coexist. But it's a temperamental standard that requires a precisely prepared water sample. You have to do it with carefully cleaned glass and specific isotopes of water, says NIST physicist Samuel Benz. Ben's group recently measured Boltzmann's constant by observing inherent noise in a circuit due to heat. Physicists measured the noise in this circuit to precisely determine the Boltzmann constant, which they will use to redefine the standard unit of temperature, the Kelvin. Dan Schmidt says the new standards won't just be a scientific improvement. Logistically, fundamental constants are a less fraught way of setting standards. The current kilogram standard, the platinum iridium cylinder, is located in a locked vault in a Paris suburb. If you wanted to calibrate a super-sensitive scale using the standard, you'd have to travel to France to find the real one or track down an actual authorized duplicate in your home country. But no country owns Planck's constant. It's part of the universe, says NIST physicist Stefan Schlamminger. Earlier this year, Schlamminger's research group published one of the most precise measurements of Planck's constant to date. You own it in the same way that I own it, he says. As long as you can build an experiment to measure it, you can calculate the standard kilogram. In other words, the recipe for making a standard kilogram will now be open access. To prove its accessibility, NIST scientists actually built a machine out of Legos for measuring Planck's constant, and it could measure a gram to 1% accuracy. Not bad for Legos. Standard units of measurement have always been about égalité. The metric system was born from the French Revolution. One of the very early sources of anger of the people in France was the lack of a universally fair measuring system, says Martin Milton, the director of the International Bureau of Weights and Measures, a suborganization of CGPM. Farmers wanted to be able to trade with neighboring towns. If buyers and sellers could weigh grain against a standardized quantity, both parties could protect themselves from swindlers. Today, standards are still about buyers and sellers getting a fair trade. You might never need to know the exact definition of a second or a kilogram, but clockmakers and scale manufacturers sure do. They have to calibrate their products against a standard. They might use a less precise, industry-approved standard, but they still have to be able to confirm that standard is derived from the most rigorous international one. A car manufacturer could then use that scale or clock, for example, to test the safety of that minivan you've been coveting, ensuring that you get a fair deal. And what's fairer than a cesium atom or Planck's constant? Humans didn't invent or engineer them, nature did. These basic building blocks can't erode or enlarge. They're the same wherever you are in the world, or the universe. Planck's constant takes the same value in a lab in Gaithersburg, Maryland, or in a spaceship orbiting Alpha Centauri. Standards scientists like to tell a nonsensical parable about aliens to illustrate the universality of these constants. Say you met some aliens, and you wanted to make some small talk. Maybe you'd talk about the weather, what clouds are made of, what rain looks like. But first, you need to tell the aliens what units you're using. They can grab a cesium atom and realize our definition of time, says Newell. Then they can go fire a photon and understand what a meter is. Intergalactic diplomacy would have to begin there, because fundamental constants are the closest we have to a universal language. Correction at 6:40 p.m. on 8,300,2017. An earlier version of this story referred to the kilogram as having 6 duplicates. There are more.